So I made this video the other day in which I was seeing if I could calculate the diameter of the moon's shadow on the Earth during a solar eclipse. After putting the video up, I started to play around with the math a little bit more. In the original video, I only considered cases where the Earth, Moon, and Sun are closest to one another and when they are furthest apart. In retrospect, I think this was a mistake since the two distances have opposite effects on the shadow's diameter. Now obviously, the largest shadow will be cast on the Earth's surface when the Earth and Moon are nearest one another. However, bringing the Moon closer to the Sun reduces the length of the shadow cast. The more acutely angled and longer shadow is produced when the Moon is furthest from the Sun. I've illustrated the four situations here in order of increasing shadow size. The worst eclipse conditions occur at apogee-perihelion. Only an annular eclipse can occur under such conditions. A total eclipse will occur when the Moon is closest to the Earth, in other words at the perigee. But when these bodies are also closest to the Sun, the shadow size is at its minimum. Ideal conditions occur when the Earth and Moon are nearest one another, but furthest from the Sun. Under these conditions, the shadow cast on the Earth should be about 134 miles in diameter, according to my calculations. I wanted to make sure it was clear how I was calculating these distances, so I've included this illustration. The formula shown on the illustration reference a corresponding spreadsheet. And before closing this video, let's get Jaronism to check the math. Take it away, Jaron.
1 into 5 is 5. Naught into naught is naught. Bring down the 5 and the naught. And then bring down the extra naught. Subtract naught from naught, and naught from naught, and 5 from 5.
Doggy, you sure can cipher.